In this video, we're going to talk about limits at infinity and infinite limits. So first of all, let's talk about what do we mean by that. Limits at infinity means that I'm going to be computing what the function approaches as x approaches infinity. These types of limits are really useful in applications because oftentimes we're interested in the behavior of function as, let's say, time goes on. So for example, what will the spread of the disease eventually become? Will it plateau or will it spiral out of the control? Infinite limits, on the other hand, is not where you let x go to infinity, but rather when you're letting x go to some number and the outcome is equal to infinity. Okay, so let's take a quick look at three sort of fairly standard functions that we've already talked about a couple of times: a reciprocal function, a parabola, and a linear hill function. Okay, so because we can sketch graphs for all of them, we can actually analyze their limits both by justifying and reasoning out, but also by taking a look at the graph. The reciprocal function has a graph that looks something like this, okay, on both sides. X squared, of course, is our standard parabola, and this guy is a linear hill function, which means that near the origin it exhibits a linear behavior, and then, as we've talked about before, it approaches some horizontal asymptote. Now this is what we're going to try to write down a little more rigorously today. Okay, so let's compute the corresponding limits for these functions. So 1 over x, the first limit we're asked to compute is as x goes to 0 from the left, which means that it's approaching 0, but from the side where x is less than 0, so from this side, right? So if I'm following the graph from that side, I notice that the closer I get to 0, the further down my graph goes. So this limit is equal to minus infinity. No matter how close I get to 0, my graph can be lower still. So it's important here to note the statement that's written above. And I would like you to think of that every time you think of the word infinity. It's not any particular number. It is a concept of a value that is larger than any number you can think of. So no matter how big you pick your number here, I can get closer to 0 and beat you on the graph even further down, okay? On the flip side here, if we take a look as x approaches 0 from the right, so now we're looking at how it comes up to here, we can see that I can get closer and closer to 0, but the closer I get to 0, the higher my graph goes. So this limit is equal to infinity. And this is the infinite, or limit at infinity. So these guys are infinite limits because in the end, their answer is infinity, but here it is my x that goes to infinity. So I'm wondering, as x keeps going and going, right? So if I were to actually label my axes here, as x keeps going and going and going, what do I expect y values to become? And I can see from the graph here, they get closer and closer to 0. I can also see that from the formula. The bigger I plug in the number for x, the smaller my outcome will be. So if x is 1,000, the fraction is pretty small, 1 over 1,000. If x is 1,000,000, it's even smaller. The bigger the denominator, the smaller the entire fraction. So this limit will go to 0. Now let's take a look at the parabola here. So I am asked to compute the limit as x goes to negative infinity, which means over to that side, right? So I'm following my graph as x goes to negative infinity, and I can see that no matter how far I go, my graph will keep going up and up and up. So this is also justified from the formula. If x goes to negative infinity, that means that I'm plugging a very, very large negative number for x. And if I plug in a very large negative number for x and then square it, my result will be an even bigger positive number. Okay, so this will be a positive infinity. Okay, and again, we can see that on the graph because my graph is just going to keep rising further and further up. Same for a positive infinity here. My graph over on the positive side keeps rising up, and I can reason out the same way for numerical understanding. If I plug in a really, really large number and then square it, my output is going to be an even bigger positive number. So this will also be positive infinity. For the hill function here, we're asked to compute what is the limit of the hill function as x approaches infinity. We can apply power analysis here and actually be able to write it down using notation a little bit better. So what this is saying is this limit because it's being computed at x equals infinity, we are interested in what happens for large values of x. For large values of x, remember power analysis? The larger values of x is where larger powers dominate, okay? So I can take a look at the top and the bottom separately, and I'm going to keep only the largest power on the top and the largest power on the bottom. On the top, I have no choice. I only have one thing, so I have to keep it. But on the bottom, I have x plus 1. Large values means I'm interested in large powers. X here has the larger power, so I'm going to ignore this 1 and only keep the x. Now this is also good news because I can actually simplify this fairly quickly. X's cancel and I get just k, which is independent of x. So my limit approaches k, which is the value for the horizontal asymptote here. Okay? Now thinking in terms of asymptotes, let's actually try to describe analytically using limits and our limit notation. What do asymptotes actually mean? And I would like you to think for a second, how would you describe asymptotes verbally? So if you were talking to somebody, I don't know, your grandmother, and you were trying to describe to her what is it that an asymptote is without using any real math, okay? Maybe just the graph and just the words from the graph. So maybe pause the video for a second here and think to yourself, how would you describe a vertical asymptote and a horizontal asymptote? Do you have any differences in the description? What are some of the nuances? Okay, now that you've thought about this for a second, let's actually draw a graph, right? Asymptotes are sort of an intuitive graphical concept. So for vertical asymptote, I'm going to take some value, let's say a here, and let's say this is what's going to be my vertical asymptote. If I were to draw the graph around it now, because it's an asymptote, I know that that means that my graph will approach it. I don't know if it's going to approach it at positive infinity or negative infinity, or maybe not at the infinity at all, right? And so this is where thinking about it beforehand and sort of setting an expectation would probably be helpful. So for example, is this an asymptote? It approaches the graph. Doesn't look like it's much of an asymptote though, right? We want it to eventually approach it, and once it starts approaching it, to approach it forever. So when we're talking about asymptotes, we mean something a lot more like this, right? Where it approaches it, it gets closer and closer and closer, it gets infinitely close, and you can never tell me how close it's going to get because it can always get even closer than that. It's not supposed to touch it, we're here, right? So asymptotes on the other side can be like, let's say like this, or maybe you have an asymptote that is, you know, in the other way, something like that. Right? So those are two different graphs. Let's say my blue one is g of x and this guy is f of x. So something like this will be an asymptote. How can we describe this using limits, using a limit notation? Okay? So here for the blue graph, I would say that the limit of g of x as x approaches a from the left. So I'm looking at a from the left along the blue graph. It's this guy right here. It's approaching positive infinity. And I can also talk about what happens on the right side of that asymptote. So limit as g of x, of g of x as x approaches a from the right is in this case also positive infinity. Okay, take a minute and write down the corresponding limits for f of x. And then think of, can you have a function where one of the vertical asymptote limits is positive infinity and one is negative? In the meantime, I can write the description of what it means to be a vertical asymptote a little without the limits, but a little bit more verbally. I can say that that means that f of a is undefined. Undefined. And there's an infinite jump. Okay, so not only do I have to actually approach the asymptote, I also have to have this infinite hole in it. Okay, for horizontal asymptotes, let's try applying some similar logic. So for horizontal asymptote, let's say I have a value, let's call it b, just to mix it up. So this is my horizontal asymptote here, right? And again, I want a graph that will approach a horizontal asymptote. Is this a graph for which my red line now is a horizontal asymptote? Not so much. We again want something to approach it and get closer and closer and closer as as the graph goes on, right? So this isn't quite right, but something like this would be, right? So something that approaches closer and closer and closer as the graph goes on. Okay, so how can we describe this using limits now? Okay, so as the x values go toward infinity, so let me call this function, let's call it h of x. So here I can say that the limit of my function h of x as x goes to infinity is equal to this value b. Notice that this same thing might happen but on the negative infinity side. So I could have a graph here that approaches my horizontal asymptote. It doesn't even have to be from both top and bottom, just be from the bottom, for example, on the negative infinity side. So let's call this graph, let's say k of x. So in terms of this graph, I can say that as x goes to negative infinity, it approaches b as well. I can even specify that it approaches b from the bottom here, and here it approaches b from the top and the bottom, right? So the important thing about horizontal asymptotes isn't what happens near the origin or for some small values. Think back to the Hill functions, right? It doesn't matter what happens near the origin. For the horizontal asymptote, what matters is what happens eventually for large values of x. So it's the exact same thing here. I don't actually care that it's not an asymptote near the origin. I care that it eventually gets really, really close to my asymptote, right? And so function can in fact cross a horizontal asymptote. I'm going to create a shortcut hn as long, and we're going to see how that happens, as long as it eventually approaches it. And this, I feel like, is a very big misconception about the words asymptote. We always think that an asymptote is something that cannot be crossed. Here is a picture of when a horizontal asymptote can be crossed. So let's say this is my graph. Actually, let me make the axis purple here. Okay, so let's say this is my graph, and let's say this is my asymptote. Okay, my graph can do this, and then approach it, and it will still be a perfectly reasonable horizontal asymptote, right? Because as I said, it doesn't matter what happens for small values of x. For horizontal asymptote, all that matters is what happens for negative infinity values of x and for positive infinity, okay? So you really have to look for large positive or large negative values of x, not small ones. For vertical asymptotes, the graph really cannot cross it, because let's try to draw a picture for when a graph will cross its vertical asymptote. So let's say this is the vertical asymptote that I have here, right? Eventually, the graph has to actually approach it, right? So, but can this happen for the vertical asymptote? Well, not so much, because this is no longer a function, right? And that's the biggest difference here, is that my graph can go up and down, horizontal, well, up and down, and then approach the horizontal asymptote, but it cannot go left and right and then eventually approach the vertical asymptote, because left and right, this graph no longer passes the vertical line test. So this is not a function. And this is why, when it comes to vertical asymptotes, they cannot be crossed. The function is truly undefined at a vertical asymptote, but for horizontal asymptotes, they can get crossed. In fact, they can get crossed as many times as you want, as long as it eventually starts approaching the asymptotic behavior. Jacques Monon is a French biochemist. He won a Nobel Prize in 1965 in physiology medicine. He is known for his work on E. coli and how they transport and break down sugar of lactose. He also worked quite a bit on RNA, DNA, and proteins, and for that work, he's actually known as one of the founders of molecular biology. One of my favorite quotes of Monon is, whatever can be found true of E. coli must also be true of elephants. So he studied very small organisms, but believed that his findings can be applied to much bigger ones and just a much bigger variety of animals. Okay, so let's take a look at what the model describes. The model describes how the rate of reproduction of organisms depends on the amount of nutrients available. Okay, so we would think that the more nutrients, the faster simple organisms like E. coli actually reproduce. And we will see if this function truly models what we believe to be true. So the rate R of division of E. coli cells, so this is the rate of division, depends on the amount of sugar, which is their main nutrient, present. So this is the rate of division. I like labeling things just so that I remember what they are, and this is amount of sugar. Okay, and we're asked to compute and interpret two different limits. Okay, now interpret means write out a sentence of what it is that you're actually computing, and then compute it. Okay, so first of all, let's do the interpretation step. So limit as s goes to 0 of r of s. So once again, there's always two pieces to a limit. What is it that you're computing, and where you're computing it at? So what is it that you're computing? You're computing r of s, which is the rate of division. So we're computing in the limit, what is the rate of division approaching? What is the rate of division approaching as, and then where are we computing it at? As s goes to 0, s is the amount of sugar, which means that essentially when there's almost no nutrients present. So as amount of sugar is very low. Okay, now let's actually try to compute it. So what do we have here? Let's take a more general look at the function first. What kind of function is this? Sometimes it's really hard to see the true nature of the function because of the, let's say, magnitudes of the constants involved. But notice that this thing is just one number. It's a very small number, but it's just one number. So I have 1.35s over s plus some number. So this is nothing other than linear Hill function. See, isn't that amazing? How many applications does one function have? You can change the context, you can change the values, you can change the numbers and the descriptions, but the math will stay the same. Okay, so if this is a linear Hill function, I'm trying to compute what happens at 0. First rule of limits, plug it in. So if I plug in s equals 0 here, actually let me first rewrite the limit. So limit as s goes to 0. If I plug in 0 for s, what's going to happen? Times 0 over 0 plus 0.22 times 10 to the minus 4. What does that equal to? Well, the top is 0 and the bottom is this number, 0.22 10 to the minus 4. 0 divided by a number is 0. So plug it in, worked. It makes sense too. What is the rate of division when there's essentially no food? When there's no food, E. coli cannot multiply. Okay, on the other side, so the second limit we're asked to interpret and compute is when s goes to infinity. So notice that what we're computing a limit of has not changed. What has changed is where we're computing it at. Okay, so we're still computing what is the rate of division approaching. What does it approach? Approaching as, and now as the amount of sugar goes to infinity. So there is a ton of nutrients. So as amount of sugar is very high. And again, because this is a linear Hill function, we already know what to expect in terms of an answer, but let's just be careful about plugging it in, right? So as s goes to infinity, let's look at our original function first. Oh, you know what? I'm just going to rewrite this. So this is 1.35s over s plus 0.22 times 10 to the minus 4. Applying our dominating power analysis, once again, says that for large values of s, large powers will dominate. So on the top, I have no choice. I have to keep this 0.35s. Whoops. S goes to infinity, 1.35s over. Now on the bottom, I have two pieces. So I get to decide which one I keep. For large values of x, I keep the larger power, which is this s here. So this number is going to go away. So I have s here, and now I can simplify by canceling s out, and I will see that my final answer will be 1.35. Now we have no units here. We're not actually given any units in terms of what is the rate computed in, but the rate here is a number, And we know that this is the number that it will approach as it has essentially infinite amount of sugar. There's, of course, some limits to how fast E. coli can reproduce, even though the amount of nutrients is essentially infinite. There's just some natural boundaries on how fast the cells can divide, and this is essentially the fastest they can divide because the amount of nutrients is as much as they want it to be. Let's again connect the graphical understanding of asymptotes to the analytical notational representation. So here is a function, we're going to call it f of x. We are not giving the formula for the function is given to us purely graphically. I would like you to pause the video here and write as many limits involving infinity as possible that you can about this particular function, thinking about not even necessarily in terms of asymptotes, but what kind of behavior do we see here at infinity and for infinity. So pause for a second, come back, we will go through this together. So while you don't have to think about it in terms of asymptotes, you obviously notice clear patterns. The horizontal asymptote exists at the x-axis for large negative values of x and for large positive values of x. So in that sense, we can write two limits involving infinity. As x goes to infinity, the function approaches the x-axis or the height of 1, and as x goes to negative infinity, we see the exact same kind of behavior. So this defines the end behavior for the x going to infinity. But we also have vertical behavior when it comes to infinity. So these pieces seem to tend toward positive infinity near points 2 and 4. So I can describe the behavior near those 2 points from both the left sides of each and the right sides of each one. So I will have that the limit as x approaches 2 from the left of my function goes towards infinity. The limit as x approaches 2 from the right of my function is also approaching infinity. And I can actually write the exact same expressions, but for x approaching 4 from the left and from the right. These are just about all of the limits involving infinity that I can write about this function. Of course, there is many, in fact, infinitely many limits that I can write about this function in general, but these are the only ones that are when x tends to infinity or when the limit itself is equal to infinity. Let's now work with the functions analytically. So we will think about how can I determine vertical asymptotes if I am given the actual formula for the function. So let's start from the beginning here. We're asking here, what is the limit as x approaches 0 of 1 over x? Because our graphical understanding of limits so far is stronger, let's actually draw the graph of this function, 1 over x. 1 over x, if you remember from your standard pre-calculus shapes, is going to look like this. This is my function 1 over x. So what happens as x approaches 0? Well, as x approaches 0, I am looking at coming towards 0 from the left and from the right, and I actually notice that it has two different answers. When it approaches from the left, if I follow the function, I will see that my height, my y value, drops towards negative infinity. If x approaches 0 from the right, then following the function, my height, my y values, approach positive infinity. So depending on whether x comes from the left or the right, I'm going to have either plus or minus infinity. Now, what about the next one? X approaches 0 of 1 over x squared. So once again, we're going to recall what the graph of 1 over x squared looks like. And if you don't remember, feel free to use Desmos to sketch the shape, but this is something that probably should be, on your short list of the graphs that you recognize. So 1 over x squared will look like this. It's sort of the same shape, but it's going to be only on the positive side because no matter what x I plug in, x squared will turn into a positive number. 1 over x squared will, of course, be a smaller version of the same positive number. So now, looking as x tends towards 0 of this function, we once again can approach from the left and the right towards 0. And notice that in this case, the graph will always be approaching the positive infinity. So, given this information, What can we say in general about the graph of 1 over x to some power k as x approaches 0? This shouldn't come as a complete surprise that these two shapes describe the general qualitative behavior of the graphs of 1 over x to the odd power and 1 over x to the even power. So odd power reciprocals will always look like this. So we're talking about 1 over x to power odd here will always have this particular shape, whereas even power reciprocals will always have the same shape as 1 over x squared. So that means that using simply these two graphs, I am able to talk about the behavior of 1 over x to power k as x approaches 0. If k is even, then my graph will look like this, and towards 0, the behavior is going to approach infinity. If my graph is to the odd power, then depending on whether I approach 0 from the left or from the right, I will either have a positive or negative infinity. So feel free to fill in this information a little bit more detail here. I am simply going to write plus or minus infinity here, and in a particular case, you get to decide which it is, plus or minus. So recalling the definition of asymptote, of a vertical asymptote that we came up a few slides ago, remember that what we need is the value of the function at some point to be undefined and to have an infinite jump near that point, which is exactly what happens on both of these graphs, and therefore on all the graphs of the form 1 over x to some power, even or odd, right? So we have these limits of the right format. X approaches some number of the function that we're interested in, and the limit is actually equal to infinity. This is what essentially signifies an asymptote. But we're going to have to be a little bit more careful than that. So let's take a look at a few other examples. So here I have x approaches 7, 1 over x minus 7. So first of all, let's recall the first rule of limits. The first rule of limits is to plug it in. The only reason I didn't do it here is because it's immediately obvious that I would be dividing by 0. Plus, I wanted to really draw on our graphical understanding of these functions. So here, if I put in 0, I'm going to get 1 over 7 minus 7. So that is, once again, 0. And what I have now is I'm dividing 1 by a very, very small number. If x approaches 7 from the left, so it's a little bit less than 7, then what I have here is a negative number, so this will approach negative infinity. If x approaches 7 from the right, this would be a number just a teeny tiny little bit bigger than 7. It will approach 7 from the right, which means that this will be a positive number, and so this will result in a positive infinity. But either way, this is either plus or minus infinity. And so this once again tells us that x equals 7 is a vertical asymptote because the limit near 7 tends towards infinity, and at 7 the function does not exist. Okay? Now, if you wanted to draw a graph of this function, that's fairly straightforward. It's actually going to be of the exact same shape, but shifted 7 units. And I will leave you to think about whether it's going to be shifted 7 units to the left or 7 units to the right. But whatever happens, the vertical asymptote actually shifts together with the entire graph. So even that alone should give you a clue which way the graph actually shifted. Now, it's really easy to fall into the trap of thinking that just because the limit is equal to infinity, it means that we automatically have a vertical asymptote. That is simply not true. So the answer to this question is a definite no. And here's one very simple example. Let's take a look at the limit as x approaches infinity of x cubed. Again, plugging it in, I can see that I'm going to have infinity raised to power 3, so a large number getting even larger, I'm going to have infinity. But just because it is easy to do, let's draw the graph of this function here. So I have that the x cubed graph is my sneaky little shape here. And of course, as x tends towards infinity, I will be looking at following the function and getting larger and larger values here. I can see that with larger values of x, I will be getting larger values of y. So this limit is of course equal to infinity. However, I can clearly see that this graph of x cubed does not have a vertical asymptote. it is missing that asymptotic behavior of approaching something very, very closely. It's not approaching anything very closely because the calculation occurred at x equals infinity, not x approaching infinity, not x approaching a specific fixed number. Infinity is not a number. A vertical asymptote has to occur at a number. So, in order to find a vertical asymptote, we need to find a spot in our function where x approaches some kind of number and the resulting limit is going to be equal to infinity. And we can see from these examples up above here that one very simple case is going to be a rational function, like all of these functions, where x approaches the value that makes the denominator equal to 0. Right? Because in that case, I'm going to end up with specifically 1 over 0, which means that my limit is going to be either positive or negative infinity. And this also means that the function is undefined at that point, which is precisely when vertical asymptote is formed. So one simple case, and essentially the only case we're actually going to consider in this course, is vertical asymptotes are produced, in particular, like there's other cases, but again, we're going to focus on this one, by a rational function. So we have a numerator and the denominator. And our favorite case of denominator being 0 is exactly where we will have a vertical asymptote. When x approaches a value that makes denominator 0. Now, of course, though, you're going to have to be a little bit careful in all of these cases because this only really works if I already have a simplified version of my rational function. If I have something like x, let's say x squared minus 1 over x minus 1, although at 1, it seems that I fall into this case, the simplified version of this function actually does not have an asymptote. Okay, so this is a very general case. For any particular function, you're going to have to go through separate calculations to ensure that you indeed have a vertical asymptote. Now, how about horizontal asymptotes? So in case of vertical asymptotes, we're looking at x approaching a number. In case of horizontal asymptotes, we're looking at x approaching infinity. And in many of these cases, we're literally going to be comparing infinities of the compositions of the function on the inside. So here, as x approaches infinity, if I plug in, what do I get? Well, if x approaches infinity, then x cubed certainly approaches infinity. It's going to be an even bigger number. Plus, x approaches infinity, so it's going to be infinity. It's some, if you think of, for the sake of plugging in, quote unquote, x approaching infinity as x being a very, very large number, then this is a very, very large number plus another very large number. So their sum, of course, is going to be also approaching a very large number. What about the next case here? I plug in infinity here, so x approaches infinity, which means that I have infinity here. And then I have times, and then what's going to happen with the square root? So x approaches infinity, so I essentially have infinity squared plus 1, so this is a very big number. Taking a square root of a very big number is still going to be a very big number. So I have infinity times infinity. A large number times a large number will produce a large number. So in the case of addition or multiplication, there are no issues. Issues will arise with subtraction, because if I have to subtract infinity from infinity, I have to reason out which of these infinities is bigger. And that's exactly what's happening in this next case here. So I have infinity minus infinity, and if the first infinity is bigger, then the answer might be infinity or some kind of number. If the second infinity is bigger, the answer might be negative infinity or some other number. So the question here is, which infinity is bigger? And the answer can really be 0 is the answer, 0 or infinity or some kind of number. It really can be any one of these three different cases. Okay, so in order to see this, now of course you can actually justify this using the dominating power analysis, because as x approaches infinity, we're looking for large values of x. So in this polynomial, for large values of x, large powers will dominate, which means that I will have the x cubed as my dominating term, and I can simply ignore the x, which will leave me with the limit of x cubed, which will be simply infinity. But if you wanted to go through and simplify the expression to try for a different approach, let's see what we can do. So I can take out the x here, and then I'll have x squared minus 1 left over. And now that it looks a little bit different, in fact, it looks like the multiplication that we've seen before that we had no issues justifying in terms of infinities, what do I get here? Well, if I sort of plug in infinity here, I'm going to get infinity times, and then what is this? X approaches infinity, so x squared approaches infinity. Infinity minus 1, well, 1 is just a number. In fact, it's small one even by the scale of numbers. So infinity minus 1 is simply just infinity. So I'm back in the case of infinity times infinity, which results in the approaching of infinity. But again, using the dominating power analysis, you wouldn't have to do any sort of arithmetic. You can simply immediately state that this limit is equal to the limit of x cubed, which will approach infinity. But in other words, this also tells you that x cubed, this simplification technique, is another way of assuring that x cubed in fact dominates over x when x approaches infinity. So let's write this down. So this shows this x cubed dominates x as x approaches infinity, because it turned out that this infinity is much larger than this one because the final answer was infinity. Now let's take a look at this more complicated example that involves square roots. So I have x minus square root of x squared plus 1. So this is actually kind of like this example, but instead of the multiplication, we have a difference. So if I plug things in, once again, I will have infinity minus infinity, and we have the exact same issue we had before. Which infinity is bigger? Am I subtracting something smaller from something larger, or the other way around? So here the question remains, and I am not able to tell you the answer right away. I really have to do something about this expression. Okay, now the square roots are always hard to justify things with. So how do we get rid of this particular square root? Remember that one technique of eliminating square roots is to multiply by a conjugate, and that's exactly what we're going to do here. So I have x minus root x squared plus 1, and I'm going to multiply this expression by x plus square root of x plus 1. And in order to keep my equality, I have to divide by the exact same expression. Now I can think of this first part as the fraction with 1 as the denominator, which means that I can in fact combine the numerators of these two functions, and opening up all the brackets, what I'm going to end up with, and I encourage you to actually go through and check for yourself these are the proper calculations, I will end up with just -1 on top, and on the bottom I will have my entire conjugate restated. Now that I actually have myself a fraction with the constant on the top, I am actually in good hands, because let's try to plug it in again and see what happens. I know that no matter what happens, on top I'm going to have a number, so I will actually end up with the answer at this stage immediately. Because no matter what I divide by, whether it's 0 or some kind of number or infinity, I will be able to immediately state what the final answer in this case is. Okay, so -1 divided by, so what do I have here? If I plug in x equals infinity all over the place, I'm going to have infinity plus infinity, which is of course infinity. So -1 divided by infinity. If I take -1 and divide by a very, very large number, my final answer will approach 0. So what does that mean? That means that my two terms here in the original difference were approximately equal, because I subtracted one from the other and I got a 0. The only way that happens is if they are actually approximately the same. They can't possibly be exactly equal because I'm looking at it for very, very large values of x and not necessarily all values of x. But what this actually implies is that for x approaching infinity, we have that x is approximately equal to x squared plus 1. Now that's also not terribly surprising because look, if I just At infinity, this plus 1 is really not going to make any difference at all. If I'm adding 1 to like a million gazillion, then it's not going to actually matter, right? So I can simply ignore the fact that it's there. And then the square root of x squared is simply going to be x, which is exactly what this approximation equation shows. Let's take a look at more examples of the limits of rational functions and how we can justify what they are. There are a few different methods, and I will show you both of them, and I will strongly advocate for one. So those of you who have taken calculus before, or maybe pre-calculus where you've actually seen limits being introduced, whenever you have a rational function, a go-to method is to take both top and bottom, and so this is my first method, and divide by the highest power. By the highest power. Okay, so what is that going to yield? I have x approaches infinity. The highest power of both of those terms combined, it has to be the highest power of the entire rational function, is x cubed. So I'm going to divide the numerator by x cubed, and I'm going to divide the denominator by x cubed, which essentially means I've actually done nothing. So my equality will still hold. Now, okay, well, let me write this step down. So 2x cubed minus x all over x cubed divided by 5x cubed plus 7 all over x cubed. And what I'm going to do in the next step is I'm actually going to undo the common denominators on the top and on the bottom. So what I'm going to do on the top is break up this fraction into the left part and the right part, right? It's kind of like splitting apart the common denominators if I've ever done common denominators. So I have 2x cubed over x cubed minus x over x cubed all over, and I'm going to do the exact same thing on the bottom. 5x cubed over x cubed plus 7 over x cubed. And now I notice that this is very convenient because a bunch of x cubes will cancel. Here I'm going to have a cancellation of one of the powers. So altogether I'm going to end up with a much smaller powered limit. So here all I have left is 2 minus 1 over x squared. And then here I have 5 plus 7 over x cubed. All right, now that I've actually simplified away my highest power division, I'm going to take a closer look at the terms that still involve x. Remember that x approaches infinity. If x approaches infinity, what does 1 over x squared approaches? I'm dividing 1 by a very, very large number, which means that this term approaches 0. And for the exact same reason, this term also approaches 0. So what I have altogether now is I got rid of the two terms that have x's because they go towards 0, each one of them. All I have left are these constants. So overall, my limit is equal to 2 over 5. Okay, so this is one approach. The dividing by the highest power will always work if you're looking at the limits at infinity of a polynomial divided by a polynomial function, a rational function. However, as you can see, there's a lot of simplifications involved, a lot of algebraic manipulations, and a lot of room to make little, silly, small mistakes. So you probably can guess that this is not the method I'm going to advocate for. The method I'm going to advocate for is a different one. So the different method is power analysis. It is much cleaner, leaves a lot less room for mistakes, and is something that we've already seen. So remember how we've analyzed the Hill functions for the behavior for large values of x, is to say that we're going to take a look at the top and at the bottom separately and apply the power analysis to each one of them. So what am I going to have here? On top, I have two terms. For large values of x going to infinity, the larger power will dominate. So out of these two terms, the larger power of x occurs in the first term. So in the limit, that's the term that's going to matter the most. Okay, and then I'm going to do the exact same thing on the bottom. So on the bottom, I'm going to take a look at my polynomial. For large values of x, the largest power will dominate. In this case, the power that has the term that has the cube. Okay, now that I've
only kept the highest power of the top and the highest power of the bottom, I can of course see that I can cancel some things out. In particular, I can cancel x cubes, and altogether then I have limit as x goes to infinity of 2 over 5. A limit of a constant is just a constant itself, so 2 over 5. See how much cleaner and faster that is than dividing by the highest power method? It allows you to immediately jump to the final answer without having to go through hoops of algebraic manipulations. Okay, so again, I strongly advocate for the power analysis method, not only because we've already seen it and we already know how to use it, but also because it avoids all of this algebraic manipulations that introduce a lot of different possibilities to make mistakes. So we can do the exact same thing for the two other questions. I encourage you to pause the video right now and try both of these for yourself using the power analysis so you can see how that works. Okay, so using the power analysis for both of these questions, now I should point out that dividing by the highest power will also work, but I'm not going to go through the trouble of writing all of this out. I'm going to go with a cleaner and more efficient method. So for power analysis, let's only make a quick note that as x goes to infinity, the larger power will dominate. So we're going to keep the highest power of the top and bottom, okay, separately. So maybe I should point that out separately. Okay, just like once again we did in the analysis for the Hill functions. So I still have my limit because I haven't computed it yet. And what do I have on top? I am picking between these two terms. Between these two terms, the highest power belongs to 2x cubed. So that's the term that I'm keeping. Looking at the bottom, the highest power is 4th. So I'm going to keep the term 5x to the 4th. Do notice that you actually have to keep the coefficients because they might slightly affect your analysis. So now I can see that I can cancel x cubed and almost all of the x's here to end up with limit as x goes to infinity 2 over 5x. Now this is a very simple function. So at this point, I'm going to stop and think of plugging it in. If I plug in infinity on the bottom for x, what I'm going to end up with is 2 divided by infinity. So 2 divided by a very, very large number, which is tending towards 0. Okay, so again, instead of going through the hoops of the algebraic, hoops, I can simply manipulate my function using the power analysis to be much smaller and then use the simple division to justify the value for the limit. And then finally, this last one, similarly using the power analysis, I can say that this limit is the same as the limit where I only keep the highest powers. So what I have here is 2x to the 5th is the highest power on the top, 5x cubed is the highest power on the bottom. I notice that these will cancel out, and what I'm going to have left is the limit as x approaches infinity of 2x cubed, over 5. Okay, now again, this seems that it's been simplified as far as it can be simplified. So my next step, I'm going to plug it in again. So plugging in infinity in for x, I'm going to get 2 times a very large number divided by 5. Dividing a huge number by 5 is not going to make a difference. So the answer overall here is still infinity. Okay, and in fact, these are the 3 different potential cases for the limits at infinity of a rational function. I will either get a number, I will get a 0, or I will get an infinity. So let's think about when each one of these happens. Take a moment, pause the video, and then look at the general shapes of these functions producing these results. Do you notice a pattern? Can you tell me what the general rule of thumb is for when the limit of a rational function will tend towards 0, for example? Or what happened here that made this limit tend towards infinity? Think about that for a second, and then let's discuss. So let's say I have a very general case of the limit as x goes to infinity of a polynomial divided by a polynomial, so a rational function. Can I come up with some kind of rule for what that limit might equal, given our experience from the previous slide? Let's take a quick look here. we noticed that when we ignored lower degree terms, if the higher degrees matched up perfectly, I ended up with a number as the answer, and the number being the exact ratio of the coefficients because the highest powers simply canceled each other out. In the next example, when the lower degree terms got cancelled, I was able to cancel the x's, but some remained in the denominator. And because x goes to infinity, the denominator grew larger and larger, so the final answer was 0. And in the final case, ignoring lower degree terms meant that what I kept was something that after cancellation ended up with the present powers of x on top, which as a result gave me infinity as the answer. Just notice that I made a mistake after all, it's 2 here. Okay, so this is going to be our general rule. All I have to do is look at the powers of the top and the bottom. And that, of course, is due to the power analysis. So as per power analysis, as x goes to infinity, highest power dominates. And therefore, it's the only power that is going to remain in my consideration. So we only need to consider the term of the highest power with highest power on the top and on the bottom. So the term of the highest power is, we also call it a degree, the power itself, we call the degree of the polynomial overall. So if the degree of the top polynomial, so the degree of the top is equal to the degree of the bottom, so degree of P is equal to the degree of Q, then this is my first case. And in this case, the limit as x approaches infinity of the rational function is going to be equal to the ratio of coefficients of highest degree terms. And then I have 2 other cases. I have the case if the degree of the top is less than the degree of the bottom. And finally, the case that the degree of the top is bigger than the degree of the bottom. These are really my only 3 cases because these are the only 3 possibilities. If you're comparing 2 values, they're either going to be equal, or one is going to be less than the other, or vice versa. So then, in this case, what can I say about the corresponding limits? I'm still trying to actually justify what the final limit is going to be. So let's go through a little bit of justification here. If the degree of the top is less than the degree of the bottom, then the term I'm going to keep on the top is going to be smaller in the degree than the term I'm going to keep on the bottom, which means that I will end up with something like a number up here and x to some power, maybe a number and then x to some power on the bottom, which means that overall I will be in the situation of 1 over infinity and hence 0 as the overall answer. In this case, if the degree of the top is bigger than the degree of the bottom, it means that on the top I will keep some x's and the bottom is going to turn into simply a constant, which will result in infinity as the overall answer. Now, while this is a really great rule, this rule is probably not the one you want to memorize, okay? I know a lot of people try to commit this to memory or write it on their cheat sheets or whatnot. I strongly recommend not doing that because it's really easy to derive and it's really easy to misremember, okay? Just remember that if you're applying the power analysis to all of these 3 cases, the actual calculations are going to be really short. And if you manage to remember the rule properly, you can simply check that your answer matches the rule, but I encourage you to actually go through the justification instead of trying to apply the rule that, once again, you have an opportunity to simply misremember. Now let's take a look at an application of the asymptotes to one very particular case. So what we have is the rate at which wolves kill moose, and it's given to us by this particular function. Now, this we already should recognize as a function of a particular form, This is a linear hill function. Now, also remember that this matches what we talked about a while back about the predator-prey dynamics. Wolves are the type of predator whose predation rate actually matches a hill function. They hunt to obtain the prey. The prey is not constantly present, but eventually they get satiated and reach some kind of fullness limit. So this is given to us in terms of moose density in numbers per square kilometer, and it actually represents the amount of moose killed per wolf per 100 days. We are asked to find and interpret all biologically relevant vertical and horizontal asymptotes, as well as sketch the graph. Again, as you've already seen me do, because this is a linear hill function, we already have a pretty good idea of what the overall shape of the graph should look like. But let's go through the analysis and see how that matches up with what we know the graph is supposed to look like. So first of all, let's take a look at the vertical asymptotes. This is a rational function, so we expect our vertical asymptotes to be where the denominator is equal to 0. So in this case, what we have is 0.46 plus x is equal to 0, which means that my vertical asymptote is going to happen at x being negative 0.46. Now, of course, this is not biologically relevant. X stands for the number of moose per square kilometer, and it cannot be negative. So while this is not biologically relevant, I am going to sketch it on the graph just to see how I have to curve my graph to actually match the corresponding behavior. Okay, so I can already start on a simple sketch of my graph. Let me do it in the corner here. There we go. And I know that I have to only sketch for positive values of x and y. But again, having a extra asymptote here will simply let me curve my function a little bit more properly. So again, not really doing anything to scale in a sense. I'm only interested in mostly the qualitative behavior. But this is going to be my vertical. It's not terribly vertical. It's a little slanted the way I drew it. There we go, much better. This is my vertical asymptote. Let's talk about the horizontal asymptotes. So the horizontal asymptotes, we always calculate by letting the function, by calculating the limit of the function as x approaches infinity. So I simply take my function and I'm going to take its limit. Now, again, I can employ the rule that we came up on the previous slide, or I can go through the justification of the power analysis of keeping the highest power on both the top and the bottom. On the top, I have no choice. I only have one term. On the bottom, I'm keeping the highest power term, so x. Next up, I'm going to cancel both of those x's, and overall, my limit is going to be 3.36. So what does that actually mean? What I did was I took the limit of my function, so the number of moose killed per wolf per 100 days, as x, the moose density, was going towards infinity. So if the moose density is going towards infinity, it means that the prey is abundant. It's of course not actually going to be infinity. It's just going to be basically present, and wolves don't have to hunt. They're just able to find the prey every time they step out of their, I was going to say house, wherever wolves live. That means when prey is abundant, wolves kill approximately 3.36 moose per wolf per 100 days. 3.36 moose per wolf per 100 days. Now, of course, you notice that this is a fraction and they can't actually kill 3.36 wolves, but it's per wolf per 100 days. So it is some kind of cumulative average there. Okay, so now I can actually draw this as the asymptote. 3.36 is my horizontal asymptote right here. And again, knowing that this is a linear hill function, I can also reason out that near the origin, the behavior is going to be 3.36 over x divided by 0.46. So it's going to be linear near the origin. And I can actually draw this function like this. Actually, maybe let me indicate the linear behavior near the origin a little bit stronger. That's my linear behavior near the origin. And then I know that I have to fit in between these two asymptotes as well as follow the linearity near the origin. So I'm going to start over here, follow the linear behavior, and continue to approach my horizontal asymptote. Looks great. If you wanted to be a little bit more precise on your graph or have any other information on your graph, you can of course plug in various points. So you can plug in some value for x and figure out where your corresponding value of y is going to be to give you a little bit more information, a little bit more precision on your graph. One thing that is always a good idea to find and is always easy to find are the x and y intercepts. So let's do it here for sort of the comprehensiveness of this example. The x-intercept we find by setting y to be 0. So my y is 3.36x all over 0.46 plus x. I set this to be 0, and now I have to pause here for a second and think. I have a fraction, it's equal to 0. The only way a fraction is ever 0 is if the top of it is 0. So what I actually have is 3.36x is equal to 0, which of course implies that x is equal to 0. So my x-intercept here is the origin. Not surprisingly, if I compute my y-intercept, for y-intercept it's actually always easier. We simply set x to be 0, so I plug in 0 into here, and I'm going to end up 0 divided by 0.46, which of course ends up with y being equal to 0. So my x and y-intercept is the origin, which already is present on my graph. Okay, so all excellent news, and here we have another usage of the linear hill function, except for now we're able to discuss its behavior, its end behavior in terms of horizontal asymptotes, and also think about the vertical asymptotes that are present if they are in fact biologically relevant. One more thing I'm going to draw your attention to, because this will come up in various points within the course, is once again how we actually calculate vertical and horizontal asymptotes, and in particular vertical and horizontal asymptotes of the rational functions. For vertical asymptotes, we set the denominator of the rational function to be equal to 0. Notice that a function has to be rational for this technique to work, but those are mostly the functions that we're going to be dealing with. For horizontal asymptote, we always take the limit as x approaches infinity of the entire function, because we want to know what the entire function approaches eventually for large values of x. Generally, if the function is simply defined mathematically and not within a specific context, you also have to take the limit as x approaches negative infinity of your function. Here, that didn't make any sense to do, so we did not actually perform that step. But if the function is simply given to you as a formula with no explanation of what it describes, you would have to compute both limits. So, short story, vertical asymptotes, denominator being set to 0, horizontal asymptotes, compute the limit as x approaches infinity.